for the night. And thanks, everybody. Welcome to the July 2023 meeting for the Tucson Amateur Astronomy Fundamentals Special Group Interest Group. Tonight, we have two presentations up for us. One is by club member Pete Hermes, who will be giving us a brief biography of, I believe, Sir Arthur Eddington.
Correct. And
following that up will be Doug Smith, who will be presenting on I believe, from the way you sounded the presentation, Doug, it's going to be on the various units and measures used for astronomical distances, and maybe about some of their origins and why they're there.
It's all about how we measure things, the distance ladder, if you want to call it that. How do we measure stars? How far away? How do we measure how far away galaxies are, and so on?
So, with that, Pete, you should be a co-host and should be able to present whenever you are ready.
Okay. Let me move stuff off to the side. And application. Okay. Trying to move the bars around a little bit, but hey, good evening, everybody. As usual, it's always a pleasure and honor to provide a presentation to y'all. Tonight's topic, one that Connor helped select for me, Sir Arthur Stanley Eddington, is actually pretty interesting. I had never really heard about Professor Eddington up until I started the research on him, but I think he's a rather interesting individual, very fascinating, a very prominent figure, no doubt, moving into the early parts of the 20th century. But like I say, it's always an honor to present before you. I hope everybody can see the screen. And I like to consider this a discussion, so please interrupt me with any questions. I may see a hand held up. I've got the top bar up there, or just activate your mic and scream at me and we'll do it. Like I say, this shouldn't go on too long. I don't want to let it drag too much. But please interject if you have a question or if you see something that I have glaringly wrong. Anyhow, Sir Arthur Eddington is probably one of the more, I guess famous is probably the best way to put it, but certainly in the UK, in Great Britain, probably one of the most famous astronomers, physicists, mathematicians, and I would say probably a scientist. Certainly not. I would consider him on par with Newton, certainly, especially considering how he was able to advance the science of astronomy. And there's actually a couple of other things he did, and this is why I found him to be quite an interesting fellow. But we'll go ahead and jump right into it. If I can get my controls to, there we go. Okay, so basically I'm going to cover a little bit of one of the interesting things, and I've made a couple of presentations on astronomers, but this is the first one that I've been able to provide in relatively modern terms. Leading up, I was looking at some of the ancient astronomers, and of course, needless to say, there isn't a whole lot of information about their lives other than the fact they were probably born about this time, they probably died then, but very little else with respect to their life outside of what they're known for and their notoriety probably in the profession. But we do know a little bit about Sir, I'll refer to him as Sir Arthur Eddington. We do know a little bit about his life because, of course, this is, he was born in the latter years of the 19th century, but his most prominent work was done just before World War I, and probably
Did
just
you
prior
mean to advance your slides?
I'm sorry?
Did you mean to advance your slides? I think.
Not yet.
Okay.
You should be looking at one that says life, education, work, legacy.
Just wanted to make sure I wasn't stuck on a stuck screen.
No, you're fine. Hey, I appreciate it, man. But like I say, it's kind of nice to be able to deal with somebody that you can get. There's a little more information available about their life. I'll cover his education, which is some pretty good detail there, and certainly his work, his legacy, and of course we'll finish off with the references. To start off, he was born shortly after Christmas in 1882 in Kendal, Westmoreland, the Cumbria region of England. If anybody's familiar exactly where that is, please pipe on. But I'm not familiar with the region as much. But his parents were Quakers. His father, Arthur Henry, was a Quaker school headmaster, and his mother, Sarah Ann Stout. The unfortunate thing, very early in his life, he was 2 years old when his father died due to the typhoid epidemic that swept through the UK in the mid 1880s. And so it was just his mother, his sister Winifred, who was a little bit older than him, and himself. And they ended up moving from their original home where he spent the first 2 years of his life to an address, Varzin 42 Wallescote Road in Weston-super-Mare. The reason I mention that is because the home actually has a plaque on it. There's a commemorative plaque where, Sir Arthur probably spent, I'm going to say approximately at least the first, I would say 12 years of his life, with the exception, no, I'm sorry, 16 years of his life, with the exception of those first two. I'll come to it later, but you'll notice some things I keep in a chronological timeline, other ones I don't. But with respect to notable things, and there's certainly a lot more about his life, but more of his course related to his education and his work. But one thing that came out, and this can be related to his Quaker upbringing. I don't know if he was, in fact, practice, what they call it, the Society of Friends. I don't know if he was a practicing Quaker. I suspect that he might have been, but always maintained, the standards and the church teachings for the most part, because he was a pacifist and he considered himself, in fact, he made application during World War I. There were various levels of conscription, or what we might call a draft, that occurred moving in through World War I once it started. And the British certainly had different levels as they needed more and more personnel. Of course, I think most folks are aware that for the most part, World War I pretty much nearly killed off an entire generation of British men, not to mention, French and German to a certain extent too. But Great Britain was particularly impacted. And so there were various times leading up to the war and during the war that there were different levels or tiers of conscription. And so, certainly Eddington had to deal with this a couple of times. For the most part, he wanted to pursue an application as a conscientious objector, when in point of fact, that wasn't really a consideration under British law. And what ultimately happened was, both owing to his work and some of his colleagues and some of his supervisors, because at this time he was actually working, they actually put forth the fact that his work was essential, not necessarily to the war effort, but he was performing essential work and really should be excused from military service. But for the longest time, Eddington didn't see it that way. He saw himself as a conscientious objector. Nonetheless, he never did have to serve. The one thing that he did consider, he was willing to go into service as a non-combatant working in the ambulance service. So, and of course, one of the most significant things about his life, he was knighted in 1930 and received the British Order of Merit in 1938. These are pretty rare occurrences. I mean, some people may think they hand out knighthoods to everybody, but I think particularly in the early parts of the 20th century, this wasn't necessarily so. And most assuredly with the Order of Merit, my understanding is there were only a limited number orders of merit that were living at any one time. And so this was a pretty rare occurrence. Of course, as people died off, there would be further selections down the road, but it wasn't like there's a couple of hundred people hanging around with orders of merits. It is somewhat limited. And of course, the big thing is you get to have the OM after your name. But these are some of the significant things that occurred in Eddington's life before his education, and of course, much after his education, going into his work. He was homeschooled for the most part for 3 years, and then, it was homeschooled, and then followed by 3 years of prep school, which occurred when he entered Bryn Mawr School in 1893. So at this time, 84, he's basically 9 years old. He excelled in mathematics. And one thing to understand, I mean, as we get talking about this, I think there really is three main academic areas that Eddington excelled in. First was mathematics, then came physics, then came astronomy, and to a certain extent, maybe philosophy after that. But during his formative years, mathematics and English literature, and of course, he was smart enough. His scholarship, his brains were basically enough to get him to Owens College, which later became the University of Manchester. And he started that at 1898. He was only 16 years of age, and this was a pretty rare thing. It wasn't something that was normally accepted, that someone not of age, say, I'm going to assume around 18 or 19, not of age would go into a university at that point. This was a pretty rare occurrence, and there were a number of hoops that had to be jumped more or less for this to happen. But nonetheless, even at the young age, he continued to excel. General studies for his first year, and his initial area of study was physics. He was significantly influenced by a couple of notable teachers. For those that may know the physics world, you may know these names. I mean, they were certainly new to me, but Arthur Schuster and Horace Lamb, they had their areas of responsibility. Schuster with respect to the discovery of antimatter, not that he necessarily discovered it, but certainly the concept in that regard. And then Horace Lamb, who authored several texts in classical physics that were used by a number of students over the years. Education continuing, he secured his Bachelor of Science in Physics, which was awarded in 1902, and this would have been from University of Manchester. His studies at Manchester merited further scholarship, and he ended up at Trinity College in Cambridge. There he was tutored by Robert Herman to become the first, and this is another thing. I mean, this was really a big thing at Cambridge, to become the first ever second year student to achieve senior wrangler status, top undergraduate math student. He was the top math student at the University of Cambridge in his second year. Typically, the wranglers were generally, well, what we consider in their last year, second to last year of studies, but generally their last year of studies. So this was significant. And it's significant for another reason, is that typically, you'll see this in one of his work assignments, this basically got him into one of his first positions, this status as the top math student at Cambridge. But anyhow, he received his Master of Arts in 1905, and I'm trying to remember, it was just, I suspect it might have been the year after, either side of 1905. I don't have the date, but I believe he also received a Master of Science. Outside of his studies, nice thing to learn, he had a little bit of an athletic background. He was a footballer when he was at Owens at the University of Manchester. Footballer, I'm not sure if that refers to soccer or rugby, or it could be both, but I'm not sure which one. Hockey player, here again. This was when he was working his first job at an observatory, and we'll get to that very shortly. Whether it was field hockey or ice hockey, not sure. He was a swimmer, a golfer, and he was an avid and lifelong cyclist. That's one thing that I was able to establish. Where he picked that up, I'm not absolutely sure. But outside of his studies and his academic work, he did have a little bit of an athletic background.
So,
Go ahead.
correct me if I'm wrong, Doug. On those ages, he essentially earned one of the top honors at Cambridge at the age of 18, and then graduated with a master's at the age of 21, which is.
Well, I'm backing this up a little bit. Okay, so he got his bachelor's when he was 18. Looks like, yeah, this Bachelor of Science, because he was born in 84. So if he got it in 1902, he'd be 18. And then he received his master's in 05. So yes, he would have been 21.
So then he got the Wrangler status when he was in 1900. Then going by this time,
the Wrangler status probably occurred, I'm going to say, second year student,
which would put him at 16. Or no, 18.
Yeah, this would be at Cambridge, not when he was at Owens. So I suspect it was a little bit, I'm going to say it was probably 1903, 1904. So he may have been almost 20 at that point.
Okay.
Because when he had his Bachelor of Science in Physics out of Manchester in 1902. Then he went to Cambridge.
Oh, okay.
And it was that second year at Cambridge when he achieved this Wrangler status, the senior Wrangler status. So at the time, I'm guessing he would have been, based on this, about 19 or 20.
Yeah.
So
regardless, that's very
regardless
impressive.
of when it occurred, even if it occurred 4 years later, this I mean, with respect to academic prowess in science, and here you certainly have Cambridge, you got Oxford, we're talking Cambridge here. This was a big thing. So with respect to that, and it sort of makes sense when you see the type of work and the type of things that he did later in his life. It certainly makes a lot of sense, but this certainly put him on a very high level going into his master's studies, and like I say, is going to provide the impetus probably pretty much for his first job, which happened to be chief assistant to the Royal Astronomer at the Greenwich Observatory. Okay, and this started in January 1906. And this is why I put in this note here, between 1835, so there was a lot of history, legacy with this. Between 1835 and 1930s, all chief, there was generally one chief and one first assistant, but over the years, there might be more than one first assistant. There would generally be one chief, but there might be 2 or 3 first assistants, were exceptional math graduates. A lot of them were this senior wrangler. So I think that was key to Eddington attaining the job at Greenwich as chief assistant to the Royal Astronomer pretty much very shortly right out of college, at least his master's studies. One of the things he worked on, he was put to work on measuring the parallax, and I think it was for Eros, for one of the asteroids. And then he also developed a new method based on drift of background stars that resulted in the Smith Prize, which here again is another big thing.
Hey, Pete,
Yes.
he developed a new method for what?
Based on the drift of background stars, Doug, I'll be the first to admit it. I didn't fully understand it, but basically it was a method, using the parallax method, using photographic plates. They had glass plates, using the parallax method to adjudge distances.
Okay,
He developed another method for adjudging distances based on the drift of background stars. Okay. Precisely how the mechanism works, I do not know. So
Okay.
I'll admit ignorance in that regard. So anyhow, so here we have him. So he's working at the Greenwich Observatory, Smith Prize in 1907. And the Smith Prize also included a fellowship to Trinity College in Cambridge. So now you see the transition coming into Cambridge out of the Greenwich Observatory. There was still a number of years, but at one point, and one of the things, and going back to the picture here, this picture you see here is basically the lodgings he had while he was chief assistant at Greenwich. And there's a little plaque. I don't know if you see, there's a little, my arrow wasn't showing it, but just on the windows on the bottom floor, there's a little circular plaque just to the left of him. And that, of course, has a plaque about his residence there. He lived in a 2 or 3 room apartment on the first floor. And for a while, I think his mother and sister actually lived with him, I suspect, mostly when he was at Greenwich, not so much later on when he moved on to Cambridge. So anyhow, we get to about 1913, pretty much we've wrapped up his Greenwich time, because he's been promoted as the Plumian Professor of Astronomy and Experimental Philosophy in early 1913, following the death of George Darwin, the son of Charles Darwin, very famous individual, at Cambridge, in Trinity College. This is a very, very exclusive position. I don't have any information on his history at Cambridge prior to that, other than the fellowship. So I'm not sure what led into this. I suspect his work at Greenwich, and certainly, the Smith Prize and a few other things probably didn't hurt exactly what the process was to obtain this chair. But, and then shortly after that, within later on that year, he was named director of Cambridge Observatory following the death of Robert Ball, holder of the Louding Chair. Essentially, the Plumian Professor and the Louding Chair were the 2 critical positions for the Cambridge Observatory. So once both these positions were open, he was chosen to fill both of them. Then essentially he became the director of the Cambridge Observatory. And so he's done with Greenwich, moving on to Cambridge. However, going back to Greenwich, while he was there, I was able to tabulate, and I think I say over 200, approximately 243 papers. He was a pretty prodigious, primarily researcher. And I think, later on, I'll say, I don't have a lot of knowledge or information, or wasn't able to find a lot with respect to his teaching credentials, although I know he lectured, I know he talked to a lot of people, and this is something that comes out later. Late, in fact, I'll mention it now, but basically, along with all of his research work and along with all of his writings, in my mind, he was sort of like the, trying to think now, Carl Sagan or Neil deGrasse Tyson of his time, very much a promoter of science. And this will come out later. You wouldn't think that. You look at this guy, well, he's writing papers, he wrote a ton of books. When did he have time for this? And the fact of the matter is, I think that was an essential part of his work and took up a lot of his time. But nonetheless, So he authored over, like I say, and I think it was upwards of 250 papers when he was at Greenwich, mostly dealing with the theoretical aspects of astronomy. Initially, that was his focus. Being that he'd come out of physics and astronomy, most of his focus was on the theoretical aspects. It's not that he didn't do any observations; he certainly did, and there were a couple of key ones that he got involved in. But his primary focus was the theoretical side of both physics and astronomy. But anyhow, you can see the Royal Astronomical Society. He was secretary for 5 years, followed that up with 3 years as the vice president, and then another 3 years as president of that rather august group in the UK. He was elected as a fellow to the Royal Society in May of 1914. Here again, a big thing. The Royal Society, of course, recognized significant contributors to science, in the UK. And if I remember correctly, I mean, typically, most of the members are from the UK, but you would see approximately, I don't know if this happened on an annual basis then or now, but you would see about 10% or upwards of 10% of the fellowships being selected would go to foreign members. So there are people outside of the UK that were able to secure a fellowship with the Royal Society. Of course, he was awarded the Royal Medal in 1928 for his work, delivered the Beckerian Lecture in 1926. These are significant events that were covered, primarily in his biography, if you take a look at the Greenwich Observatory site. But yeah, he lectured on the diffuse matter and interstellar space. You're going to find some of his most significant work dealt with the composition and the processes in stellar evolution. Okay, so we move on to other contributions in work: astronomy, relativity, cosmology, and philosophy. And I sort of backtrack a little bit. The bulk of his work was theoretical work in stellar interiors, including the first true understanding of stellar processes. He was one of very few, I mean, just a handful, if that, that proposed theories with respect to how stars develop their energy. Most of his work began in 1916. He was one of the first to propose that nuclear fusion was the main power source for stars. And he also provided a physical explanation of Cepheid variables. He recognized the importance of ionization in stellar interiors with respect to the contribution that radiation pressure along with gas pressure made against gravity to keep stars pretty much in hydrostatic equilibrium. But admittedly, during this time, as these theories were coming out and some of these new ideas were coming out, there wasn't necessarily agreement amongst all the experts. You certainly had, I don't want to say necessarily rivals, but contemporaries, not necessarily colleagues, but contemporaries that disagreed with some of his ideas. And this is just one where Eddington promoted proton-electron annihilation and nuclear fusion processes over the Kelvin-Helmholtz mechanism. And of course, he was pretty much, in a very basic sense, proven to be more accurate with respect to some of his ideas and theories, and certainly with respect to the main energy producer in stars.
What was the Kelvin-Helmholtz mechanism? That's the first time I've come across that.
It's a good question, Connor, and I actually looked at it a little bit, didn't completely understand it. I know it varied a little bit with these, with these basic fusion processes, and I think it had to do more so with the variation of the different types of stars, because certainly, I mean, there were a couple of things that Eddington did with respect to his processes that probably fit the main range, probably, like the main sequence of stars, not necessarily the extreme, although in some cases they do, but certainly, like white dwarfs and red supergiants would have been out that realm, even though those weren't specifically studied. But to be honest with you, no, I'm not familiar with the mechanism, or not enough to talk about it, at least.
Thanks.
Okay, so these are a couple of key dates. Here again, I backtrack. This is sort of like one of those TV shows. You go forward in time, you go backward in time. And so we take a look at some other, and these are key dates, key accomplishments that sort of explain his involvement in different types of work. But one thing, in 1920, he traveled to the island of Principe to, this is off the west coast of Africa, to observe the solar eclipse on May 29th of that year, confirming part of Einstein's theory of general relativity regarding the bending of light. In other words, he was able to observe stars slightly out of position and make the case. And his results weren't very good, but they were good enough for the time to make the case for this. The expedition wasn't an entire success, but like I say, it was good enough. Prior to that, I think he'd actually made a trip. I keep thinking around. This is when he would have been at the latter years at Greenwich, made a trip to Brazil to observe another eclipse, and that didn't go very well. They weren't able to. I mean, notwithstanding the poor skies they had, some of the equipment they had, and some of the processes that they had developed really didn't amount to much. They had limited time. They were able to make some observations, but the methods and processes that employed just didn't deliver any good science. So this was a little bit better, but certainly not the best in all cases. But what he wrote about, what he was able to write up and provide, to his contemporaries was good enough to make the case for confirming part of Einstein's theory with respect to bending of light, coming by, the eclipsed sun. It could be observed, and they could actually see this effect a little bit. Eddington, here again, and I mentioned this before, this is around the 1920s, speculated that nuclear fusion processes in stars were the principal mechanism for their energy, hydrogen to helium, hydrogen fusion into helium. In 1923, and this is where we diverge a little bit, he published a mathematical theory to relativity, and this is key, which included a compilation of his lectures on relativity that provide explanations in both lay and scientific terms. And you'll see I have a picture there. There's Eddington and Einstein, and this was a meeting that took place, I think, quite a few years after that, may have been in the 1930s. Einstein made quite a few trips to the UK, lectured quite often whenever he was over there. But Eddington was probably one of Einstein's principal proponents with respect to his theory of relativity. You're going to see later on, I'm going to have a little quote here down the road, and I don't know if it's necessarily true, but Eddington was one of the very few, and I think less than a handful, that probably truly understood Einstein's theory. He had the math background, he certainly had the physics background, and this was sort of an area where he branched off a little bit, from astronomy, from pure astronomy, although there were a lot of relationships nonetheless. And he was very much a proponent of, and to a certain extent, Einstein may have proposed the theory, but Eddington is probably the one that made him famous for it, to a large extent, given how much he talked about it and the way he was able to explain it, not only to his colleagues, but to the general population, or at least those that had an interest to a certain extent, because like I say, he could explain it in lay terms also. One of the, outside of his principal work with respect to basic stellar processes, of course, another thing in 1924, he discovered the mass luminosity relationship for stars. There is something I'll get, I think, on the next slide, a specific value that's related to them, or a relationship. And then in 1926, he publishes The Internal Constitution of Stars, which was, a text that was used for a number of years by generations of astrophysicists with respect to the basic processes that occurred in stars. And if you ever take a look, and I read some of the excerpts, both journal articles and books, and don't get me wrong, I do not understand everything, but I think if I understood just a little bit more, his writing style academically was such that he was a very easy person to understand. I think that's why, he connected with a lot of people, both in academia and outside of academia. And I think that was one of his other very, very true values to the science and to the, proliferation of science, both in the UK and outside. This is one of the things, prior to World War I, when he had just started to work, he was very much in tune with the exchange of information between scientists on the island in the UK and with scientists throughout Europe. And of course, World War I pretty much put the kibosh on that and restricted that. And I think that was, he took, I don't think he felt very good about it, because one of the things, he liked interacting with his colleagues. He liked interacting with his contemporaries and exchanging information. Part and parcel how he ended up promoting Einstein's work so much, because in his work, and I think we go back when we look at his primarily his position in the Royal Astronomical Society, afforded him the opportunity to read some of the early papers, some of the early works of Einstein. And, like I said, he gained an early understanding of some of the work that Einstein was doing. And so, when Einstein came out with his full theory, it wasn't much of a stretch. And certainly we can understand why he became such a strong proponent of it, or promoter of Einstein to a certain extent. A couple of other key things, and here's the quote I wanted to refer to. Aston, this is not necessarily attributed to him, although a lot of people think. Asked in 1919 whether it was true only 3 people in the world understood the theory of general relativity, Eddington allegedly replied, "Who's the third?" Meaning Einstein, him, who's the third? But this was very true. There were very few people, probably just prior to and just after World War I, that truly understood Einstein's work. Anyhow, another thing too, and this gets a little bit into his philosophy. And Eddington wasn't necessarily a metaphysicist. He wasn't looking at the spiritual aspects of science, but pretty much he was trying to make some connections with some of these things that he was discovering, that he was, gaining an understanding of. And he was trying, most assuredly, one of the things that came out a few years after Einstein's work was, starting work on the unified theory. Einstein certainly did it. And this isn't something that necessarily happened in the 20s. I would suspect more so in the latter decade or so of his life. But he was certainly interested in working on unified theory, but he was trying to connect it with what he called a fundamental theory, trying to numerologically make determinations with respect of trying to connect the big with the little. He never got there. His work continued. I mean, there was a book that was published, but pretty much the work was unfinished. But a lot of his had to work with, trying to determine these dimensionless ratios with respect to the weight of an electron, weight of a proton. Those were 2 key values in some of the work he did, and he was never able to get there. However, one thing that he was able to determine, and it was named after him, was what's called the Eddington limit. And this is the maximum star luminosity at hydrostatic equilibrium, when the radiation pressure and the gravitational forces are in balance. Because we remember, certainly gravity is trying to bring everything down into the center of the star, and of course the radiation and gas pressures are pushing outward, and there's a balance for a long period of time. And of course, different stars, sometimes hydrostatic equilibrium becomes something else when stars either grow real big or they shrink down to minimum size. But under hydrostatic equilibrium, when there is a balance, like our sun pretty much is at this point,
So
very intense radiation driven. Go ahead.
A little bit more simplified explanation of the Eddington limit is it's the equation that dictates how big stars can get and how quickly black holes can consume material from their surrounding environment.
Yeah, because when that limit's exceeded, that provides a little bit of the explanation behind black holes, or at least accreting black holes and quasars. The limit isn't an absolute. I mean, certainly stars can be beyond that, but more than likely they're not in hydrostatic equilibrium at that point. So, but anything else, Connor?
No.
Okay, thank you. Okay, yeah, he was a prodigious writer. I can't see these anymore because my screen blocks these out. Oops, there they are. Okay, now I can see them. But you can see from 1918, and these weren't the only books. These are probably some of his more notable works. You'll notice the fundamental theory was actually published a couple of years after his death. But for the most part, he was the single author of each one of these. These were books. There were a few more, but these are probably some of his notable works. But you can see they focus on stellar composition, relativity. There's a lot of math in here, the constitution of stars. You get into the nature of the physical world. Here is some of his philosophy moving in, and certainly the philosophy of physical science. A lot of these books have been reproduced and updated publications, not necessarily editions, but have been I think there are a few are probably still in print. Okay, now I gotta try to get there we go. Okay, so moving on. Now, one of the things I mentioned, here we have this guy. He's was well educated, did a lot in his field, both in astronomy, physics. math to a certain extent. He's known for his astronomy and physics primarily. Of course, math is that background. But as far as a promoter of the science, and you take a look, here's one of his books, and it was one of the books that appeared on the previous slide. You can get a picture of when he wrote that one. But like I say, he was very much a science promoter. He was a member of the Royal Academy. He was a member of the Royal Astronomical Society. You can see here in 32, he's at an IAE, at an International Astronomical Union meeting in Plymouth, Massachusetts. There's a couple of notable names on there, but you can see it's a pretty august list. This isn't the entire attendance list, but just who this picture was taken with. But that's Eddington on the far left with some of his contemporaries. And this was very common. He lectured quite often. He lectured in a lot of different places. I think most of his work was at Cambridge. I don't think it was so much where he actually did classwork, but he lectured quite a bit, did a lot of research. But I think he was out and about, talking to people, talking to his contemporaries, talking to his colleagues, talking to anybody that would listen, that would attend his lectures. And like I say, he was able to communicate a lot of this science, a lot of this math in lay terms, understandable terms for those that weren't necessarily his contemporaries. And I think this is probably one of his most significant values as an individual, as a scientist, was being able to do that, because for the most part, you look at a lot of scientists back during this time and prior, there were very few people that could understand a lot of this work. And I think he did an outstanding job, at least at trying to make it understandable for the not everybody, but even outside of his field. And I think that did a lot to promote science into the latter part of the century. Death and legacy. Unfortunately, he passed away in 1944. So that would have been 62 years of age, roughly 61, 62. He had 13 honorary degrees from universities around the area. Most of them were science-based, physics, things of this nature. He never married, so he never had an immediate family. It was just his mother and his sister. But he never married. No small wonder, but you sometimes wonder, because he certainly seemed to be the type of individual. He seemed to be outgoing enough and not just buried entirely in his work, but maybe he was. Numerous awards and honors. I mean, you take a look at his bio listing at the Greenwich Observatory listing for him, and there's probably anywhere from a dozen to 2 dozen awards and honors. There's a lunar crater named after him, and asteroid 2761. Probably most notable, and this is, of course, in Latin, is a plaque that was placed, his memorial, at the Trinity College Chapel in Cambridge. And of course, we provide the English translation for you. Of course, there's, Sir Arthur Eddington, OM, Order of Merit. And you can see for 37 years, he was a fellow of the college, and from the start of his fellowship, and then 31 years as the Plumian professor. So a pretty extended experience, I think. He was able to find a job and stick with it, but did quite a bit of good work. And you can see they make mention at the end of the plaque, as befitted a member of the Society of Friends, here again referring to his Quaker heritage. There are my references, and thank you for your attention. Questions, comments?
That was very good, Pete. I really liked that.
Thank you, Ross.
Thank you very much, Pete.
You're welcome, sir.
So you know what, I just wanted to mention that he started off studying science, but also literature, and then he really got into philosophy and everything. And it kind of reminds me of David Levy, because he's
I don't know. I didn't get a chance to read any of those writings, but it would not surprise me. Yeah. Have you read any of his stuff? Philosophy?
No.
Okay.
No, but he seems to have been, aside from the fact that he never got married, and he seemed kind of one-sided in his life in that way, but he seemed kind of a well-rounded person, that he had a really good, a full education, as you said.
Yeah, no, I think so very much too. And that's why it was kind of surprising. But like I say, I think he dedicated most of his life to the science and promotion of the same.
Thank you very much for that, Pete. And
Okay, thank you.
Doug, we'll hand it off over to you next.
Let me see if this. That mode. Okay. So I'm going to talk about how we measure distances in astronomy, from very close distances to nearby stars, all the way out to the farthest galaxies. I'm going to talk about the different methods that we use and where they came from, a little historical background. I think a lot of amateur astronomers don't know all these methods or don't know much about them. So I thought this would be a good lecture to do, just so people might understand what these different methods are, and might be able to answer the question if they're ever asked, well, how do you know how far away that guy is, or how far away that star is, how far away that galaxy is? When you're done listening to this, then maybe you can answer that question if someone asks you. I always start off with a slide of humor. I've done this myself. Left the lens cap on. Okay, so as I said, this is a question I get asked. Even when I'm doing star parties, outreach events, I'll get asked this question, because we'll say this cluster is so many thousand light years away, or this star is this many light years away. Someone will ask me, how do you know how far away it is? And so then we have to explain. So I think a lot of amateurs don't know how to answer that question. So like I said, that's the purpose of this talk. I'm going to talk about these different methods. I'm going to try to avoid the math as much as possible. I will have a little bit of math, but nothing too complex. And so what I'm talking about is what's commonly referred to as the distance ladder, because there's different methods used for different distances. As you work out, you're using different methods. So they call it a ladder. So I'm going to go through this ladder from closest to farthest, basically. And like Pete, if you've got questions, just shout them out. So trying to figure out the distance to the things in the sky is nothing new. I'm quite sure the ancients would look up at the sky and wonder how far away the stars are, how far away are the planets, how far away is the sun. I mean, even the early Persians had at least figured out that the stars were farther away than the planets and the moon. And how did they know this? It's because they were able to observe occultations, where the moon would pass in front of a star, or the moon would pass in front of a planet, or sometimes they'd see a planet pass in front of a star, like Mars would block out a bright star, or Jupiter. And therefore they knew at least the stars were farther away. They had no idea how far away. They just knew they were farther away. It means the moon was closest. The moon was closer than the planets were closer than the stars. That much they had figured out. It wasn't until you got into the Greeks, when the Greek civilization was in its prime, that you started getting what I'd call logical attempts using math and science to try to estimate the distances to astronomical bodies. And in some cases, they were able to do it. They were able to estimate the distances to Mars, to the moon, to the sun, and things like that, but without the use of telescopes. And some of these estimates were not bad. So we're going to talk about some of these Greeks who did this. I'm not going to go into a biography of these people because a lot of these names we've covered in the past, and that's not the purpose of this talk. I'm just going to mention who they are and what they did. We all know who Euclid is. He came up with basically modern geometry, and he gave us the geometrical principles that allowed us to use trigonometry as a way to measure distances. The method that we call parallax is trigonometry. It's basic trigonometry, and he's the one who came up with the principles behind it. Aristotle. Now, Aristotle is not a name that we normally think of when we talk about astronomy. He's known as a philosopher and a big thinker and a lot of other things in Greek history, but we don't normally think of him as astronomy. Because it turns out he did some very interesting work in astronomy. He wrote works on astronomy, including a work where he estimated the distances to the planets using trigonometry, using something like parallax, and got reasonable answers, considering. And he also wrote a paper where he came up with basically what's called a Copernican model for the solar system. Now, he was laughed at, and most of the other philosophers of the time dismissed it. They didn't believe the sun was at the center of the solar system, and so his great work on the Copernican model never got much traction. But he did some interesting work, and the important thing, the reason he's included in this lecture is because he came up with estimates for the distances to the planets using something very similar to parallax. And his distances, while not perfect, were within a factor of 2, which, considering, that's not bad. Then there's Eratosthenes. This guy is one of my favorites. He was a peer of Aristotle, mathematician, student of the sciences, basically. He's the guy who computed the circumference of the Earth, and he got it pretty accurately, within 5%. And he estimated the size of the moon and the sun, and he got that pretty accurately too, within a few percent. And the circumference of the Earth is important here because that's going to be used for parallax measurements. And then there's Hipparchus. I think of him as probably the first true astronomer, in the sense that he spent most of his time observing the heavens and recording his observations. He made the first real attempt to measure stellar distances using parallax. Now, he was not able to get any kind of a good answer because he was using the diameter of the Earth as the baseline for his parallax measurements. He would 12 hours, he would look at the star, and 12 hours later, he would look at it again, and he would try to get the shift, okay? But that's too small of a baseline because we know that in modern parallax measurements, we're using the diameter of the Earth's orbit around the sun. So the diameter of the Earth is only a few thousand miles as compared to, 150 kilometers for the radius of the Earth's orbit. So his baseline was way too small. So even with his telescope, he would not have been able to measure the angles. And telescopes were not around during that time. So he was not able to get any kind of, all he could come up with is the stars must be very far away and must be hundreds of times farther away than the planets. That's the best he could do. But he at least attempted it using the parallax method. And if you don't know what the parallax method is, this is what it looks like. It's simple triangulation. You're on the Earth. like on that figure there, and you look at the star once in June, and then you look at the star again in December, and the star is going to shift positions relative to background stars. And if you can measure that angle, then you can compute the distance to the star. That's how you do measurements for close stars. And to make it, some things came out of that method. The definition for the unit parsec, that is the distance at which a star would be from the Earth if you use the radius of the Earth's orbit as 1 astronomical unit, and at a distance of 1 parsec, the angle theta, which is half of the angle that the star would shift in position, would be 1 arc second, and that would put the star at 1 parsec, which is 3.26 light years. Keep in mind, though, that when you're doing this parallax, you're measuring twice that angle, because you're measuring the star 6 months, June and December, for example. And so you're on one side of the sun, and 6 months later, you're on the other side of the sun, and you're measuring this 2 theta angle. This angle here is actually 2 theta. You're measuring that whole angle there when you do the measurement. So if the star was 1 parsec away, what you would actually see in terms of that total parallax angle would be 2 arc seconds, because you're actually measuring twice the angle. So, but this is what parallax is. For anyone who's interested in the math, here's the math. You measure the angular shift. 6 months later, you measure the star again, and you see that angular shift with respect to background stars. You use a small angle approximation to the sine of the angle is roughly equal to the angle, because it's a very small angle. And so you can use a small angle approximation, and you can get that formula down at the bottom right, which is very easy to compute. And so you can get the distance right out, and it comes out in parsecs. Now, as I said, Greek astronomers, they couldn't measure stellar distances because they were using the radius of the Earth, which they knew Eratosthenes had measured that, but that's way too small of a baseline for your parallax measurement. Even the closest star would have had a parallax angle less than 1/1000th of an arc second. So there was no way they could measure that. Certainly they didn't have telescopes, and even if they had a telescope, I don't think they could have measured it. Parallax measurements didn't start becoming useful until the time of Isaac Newton. And at that point, astronomers had telescopes, and they knew the orbital radius fairly accurately. And so they were able to start using the orbital radius as the baseline for their parallax measurements. And they were able to measure angles down to fractions of arc seconds. And so at that point, they were able to start measuring distance to close stars. However, until the later half of the 20th century, in fact, probably until the last 10 years of the 20th century, parallax measurements basically could only be done for a couple thousand stars. Because even with large telescopes, because of problems with the atmosphere and everything else, getting angular measurements down to the hundredths of an arc second was extremely difficult. And so you could only get a couple thousand of the closest stars with the equipment that was available at the time. Finally, in 1990, the Hipparcos satellite was launched. And the Hipparcos, I'm sure I'm butchering that name. the Hipparchus satellite was able to provide accurate distance measurements for over 100,000 stars, because it was able to do parallax with a precision of milliarc seconds. So down to 1/1000th of an arc second, it was able to measure positions. And so that was able to take us out as far as a few hundred parsecs now. So now we're getting a larger area that we know distances to. And then the good one that came out was in 2013. European Space Agency launched a satellite called Gaia. The Gaia was able to provide parallax measurements with a precision of 20 micro arc seconds. This allowed the distances to go as far as 8,000 parsecs, which is basically all the way to the center of the galaxy, to the galactic center, the center of the Milky Way. And basically, Gaia provided measurements, distance measurements for virtually every star down to 15th magnitude. So that's a bigger portion of the Milky Way. Parallax is considered the first rung in our distance ladder, if you like. Yes. The Harvard Observatory computers and Mary Ann Draper. I love this picture on the left, by the way. I used it a lot in several lectures. It's a really great picture. Anyway, late 1870s, a gentleman named Henry Draper started a catalog of stars using the spectral lines to differentiate the different types of stars. He died in 1882, but his wife, Mary, on the right, continued his work for a little bit. But later that year, she basically donated all her equipment to the college, to the Harvard College Observatory, and endowed the Harvard College Observatory to continue his work. Two ladies in particular in this picture down here on the left, Wilhelmina Fleming, who is in the red circle, and Annie Cannon, who is in the blue circle, worked on this Draper catalog for a number of years. And what they got out of their work and eventually published, what we know of as the OBAFGKM classification system on the spectral classes and temperature. In 1890, the Harvard College Observatory finally published the Henry Draper catalog. Then these two gentlemen came along. These two astronomers are, I cannot pronounce his first name, Ejnar Hertzsprung. That's the try I'll use, and Henry Russell. Independently, they worked on, they took a look at the stars in the Henry Draper catalog, and they picked out stars that had known distances, that is, stars that had parallax measurements out of that catalog. And they eventually came up with a relationship. They discovered that there was a relationship between the spectral classification of the star and its luminosity. Because they had measured distances, and they had the spectral classification, and they had apparent magnitudes for the stars. And since they knew the distance from parallax, they could deduce what the luminosity was. And they eventually came up that there was a relationship between spectral classification and luminosity. And if anybody doesn't know, the absolute magnitude of the star is how bright the star would appear at a distance of 10 parsecs. But anyway, this relationship was later refined over the years, and has been named after both of them. And we all know it as the Hertzsprung-Russell diagram. And if you look at this diagram, you can see that basically for the stars, there is a very tight relationship, not quite linear, but almost, between spectral classification or color, if you like, or temperature, if you like, on the x-axis, versus luminosity going up and down the y-axis, which relates to absolute magnitude. What this allows astronomers to do is that we can now look at a star in the sky, and it can be, as long as we can see it and take its spectrum, and we can determine its spectral class by looking at its spectrum, we can place it on this diagram and get an estimate for what its luminosity should be, its absolute magnitude should be, and then we measure its apparent magnitude, and based on its measured apparent magnitude and what we think its absolute magnitude should be, we can compute a distance. This relationship allowed astronomers to basically map the Milky Way, because now they can look at stars all the way to the edge of the Milky Way, determine distances, determine where they are at various distances, and basically we can create a map of the Milky Way. Now there is something else that comes out of this too, is that we can also look at stars and determine what's called extinction, how much the star is being dimmed by gas and dust between us and that star, and that also is useful for creating a map of the Milky Way. But this HR diagram is what allowed astronomers to actually start looking at the structure of the Milky Way galaxy. The HR diagram is what's called the second rung in the distance ladder. The method they call it is main sequence mapping, if you like, where you map a star on the diagram to get its absolute magnitude. Let's go back to this picture again. Like I said, I love this picture because of the people that are in it. Henrietta Leavitt, she also was what's called one of the Harvard College Observatory computers. She's the gal in the red box there. She worked at Harvard College Observatory until her death in 1921. As part of her work for Pickering, she studied variable stars. In particular, she did a study of Cepheid variables located in the small Magellanic Cloud. Based on that study, she was able to establish a relationship between the variable star's period and its luminosity. I just made a note here. Look on the wall behind her, and there's a light curve for a variable star. One of her favorites, I think. I'm not sure. So in 1912, she published a paper where she showed this relationship. See the figure there. This is from her paper. And it showed that the periods of variable stars is directly related to their luminosity. There, you notice there's two lines in this plot. One of them is a variable star. So one is the minimum magnitude. The top line is the minimum magnitude of the variable star, and the bottom line is the maximum magnitude of those variable stars. And she showed that the relationship applied to both the minimum and the maximum magnitudes for these stars. And thus, if you could measure the period of the variable star, you could again map it directly to an absolute magnitude, and then you could measure the apparent magnitude by looking at the star and thus compute its distance. What this allowed astronomers to do was to look at other galaxies outside of the Milky Way. because now you had large telescopes by this time. You had 100-inch, and 30 years later, you have a 200-inch telescope out at Mount Palomar. You could look at close galaxies like the Andromeda Galaxy or the Pinwheel Galaxy, and you could pick out individual stars. And so now you could look for Cepheid variables in those galaxies and use those variables as a standard candle, as a way to determine the distance to those galaxies. This was extremely important because this is how Hubble first was able to establish that at that time they were called nebula, the Andromeda Nebula, the Pinwheel Nebula. This was how he was able to ascertain that the Andromeda Nebula and the Pinwheel Nebula and these other galaxies were not part of the Milky Way. They were way outside the Milky Way's boundaries. And this is the method he used to determine that. The Cepheid variable method is called the third rung on the distant ladder. Type 1 supernova. This is a little bit different than the other rungs that I've already done. It's going to be out of order because this is a very recent one. Surprisingly enough, this is the newest rung, but not the last rung. So I'm not doing them in order of years. I'm doing them in distance order. So it turns out Cepheid variables make really good standard candles, but they can only be used on the galaxies that are close enough where you can actually see the individual stars. That limits you to less than 5% of the galaxies that you can look at, even with the Hubble Space Telescope. That was really too small of a sample to do a good calibration on Hubble's law, which is the last rung in the ladder, which we'll talk about. And astronomers tried to find something else, a better way to calibrate Hubble's law, if you like. So in the 1990s, you started seeing a lot of papers come out, mainly from astronomers in Chile and the United States, published a series of papers indicating that the type 1a supernova, the way it decayed after it reached its maximum brightness, the decaying light curve, might be used as a standard candle. Turns out that the way it decays is a very well-defined process because we understand the type 1a supernova really well. It has a very distinct light curve and a very predictable light curve when it decays. And they were able to come up with a way to refine the relationship and show that you could use a type 1a supernova decaying light curve could be used to estimate a distance to that supernova. The guy who really came up with this relationship and has published it is an astronomer by the name of Mark Phillips. That's his picture in the center there. On the left, there's a type 1a supernova in that galaxy. I don't know which galaxy that is. On the right is the original figure that Mr. Phillips had put in his paper showing the decaying light curve from a type 1a supernova. And there's a type 1a supernova decaying away, and you can see what the light curve is doing there. But type 1a supernovae are often very bright. In a lot of cases, they're brighter than the entire galaxy for a short amount of time. So you can see them as far as you can see galaxies, basically. You can see type 1a supernovas. And then by observing the decaying light curve, and you do some fancy curve fitting and some other mathematical manipulations, you can deduce a distance. And this allowed astronomers to, quote, calibrate Hubble's law, because now they could look at galaxies out to billions of light years away, as long as you saw a type 1a supernova. So if we try, astronomers today are always looking for supernovas because they want to catch this decay curve, because then they can get a good measurement of a distance. And it's pretty accurate. They found that it's accurate to within a few percent, as far as they've been able to tell up to now. Now, one of the things that came out of this was that this is how they originally found that the Hubble's law for the expansion of the universe didn't work, had problems. This is where they first started seeing the problems, as they started looking at type 1a supernovas from galaxies that were very, very far away, and they weren't matching up with what Hubble's law was predicting. And these are the original measurements that came out of the type 1a supernova measurements. This is where they started having to come up with theories that involved dark energy and the acceleration of the expansion of the universe. Came directly out of the measurements for here, because they didn't line up with the standard Hubble model. This is called the fourth rung. This is considered the fourth rung in the distance ladder. We'll take a step backward in time now. During the 1920s and the 1930s, Edward Hubble did a lot of work classifying galaxies, and he studied their radial velocity, basically how fast they were moving away from the Earth. He matched up his data with the distance estimates that were available from Cepheid variables, and he was able to notice what appeared to be a relationship between radial velocity and distance. So that's Edwin Hubble on the left, and on the right is a sample of some redshift for some different galaxies. The spectrum on the bottom is the laboratory at rest reference, and then if you go up, you see a nearby galaxy. The lines are shifted a little bit to the right. You go farther away to a more distant galaxy, the lines are shifted more to the red. And you go to a very distant galaxy and they're shifted way, way off to the red. And that's what he noticed. And for the galaxies that you could get with Cepheid variables, because this was before the type 1a supernova was used, he was able to match up his redshift measurements with Cepheid variable measurements for distances, and he came up with the relationship now that we know of as Hubble's law. And basically Hubble's law is actually very simple in its simplest form. It's just V equals HD, where V is the recessional velocity, how fast the object is moving away from us. H is the Hubble constant, and D is the distance. And very simple. But that law, his simple Hubble's law, is what led to the development of the Big Bang theory and the expansion of the universe that we think of today, came out of that. And I'm sure all of you probably already know this, but Einstein, his general theory of relativity actually predicted that outcome, that the universe was expanding. Einstein didn't believe it and put in a fudge factor to get rid of it. He later said that was the biggest mistake. But the law allows astronomers to compute distances for a galaxy as long as you can take the galaxy spectrum, because you can just plug it into this formula and you can measure the velocity from the redshift, and you can just plug it into the formula and you'll get a distance out. But as I said earlier, the recent measurements of supernova type 1a indicates that Hubble's law perhaps is not quite as clean as it we thought it was. But it's still considered the last rung in the distance ladder because it gives us the measurement of distances to galaxies far, far away. And the figure on the right just shows you a few of them. For example, a galaxy in the Virgo cluster. You see the spectral lines there. There's a hydrogen bomber line there, and then there's the two calcium lines, the little pair of lines right here, these lines. And then a galaxy in Ursa Major, which is farther away. It's 1 billion light years away. You see how far the lines have been shifted. And then a galaxy that's out in Corona Borealis, which is 1.4 billion light years. You see the lines are shifted farther. And you notice that the radial velocity is going up too. They're moving faster as they go farther away. Plutus, you're out at 2.5 billion light years. The lines are shifted way over here. And then there's a galaxy in Hydra that's almost 4 billion light years away. And here the K lines are almost shifted right off the spectrum into the infrared. They're well off to the right. So the Hubble's law is still used today as a way of estimating distances to galaxies. But we know that there's probably something wrong with it. So this is kind of a nice figure that I found that shows you the different methods of the distance ladder. I didn't cover the first one, which is bouncing radar off of close objects like planets. But you've got the parallax, which is for nearby stars, which is out to maybe 100 light years. You got the main sequence fitting, where you're using the HR diagram and you're fitting stars onto the HR diagram. That takes you, pretty much the whole Milky Way. You've got nearby galaxies, which you can do with Cepheid variables. You've got galaxy clusters, which go all the way out, which you can do with the white dwarf supernova, which is the type 1A supernova. And then you've got Hubble's law at the end there. So, and that's it. Questions? Comments?
Bravo, good job, Doug.
Doug, I've got a
Enlightening,
question.
I like that.
Okay, question? Who?
Doug, it's Bernie.
Hi, Bernie.
Do you know if there's a direct relationship between Z and mega light years?
Say that again.
Do you know if there's a direct relationship between Z, which is the redshift, and mega light years? I've seen Z quoted as distance figures to obviously, distant.
Well, I mean, if you look at this relationship, velocity equals hd, that's a pretty basic relationship. And the z is the redshift, right? So that's going to have a direct relationship with the v.
I've never seen a chart that had like Z and light years related to each other.
It's probably not, you probably won't see a z related to distance, but you would probably see a direct relationship between z and v in this equation here. Because the z is
generally
redshift, the z is redshift, and that's related to the radial velocity.
Yeah, but generally the theory is also, and I think this is what Bernie's getting at, is the higher the z, which is the higher the would equate to higher recessional velocity. Generally, the relationship is the higher that number, the further the galaxy is away.
Yeah.
So it may not be quantitatively, but perhaps in a relationship, Bernie. I don't think, and maybe that has been established, but the papers that I've looked at, of course, it is kind of the math is complicated. But from my understanding, it's more of a relationship. The higher the z, the further away. Does that equate to specific numbers? I have not seen that.
I've never seen it. I've always been curious about that.
Yeah, it's just now that they're trying to, Hubble started it, and I think the expectation was with James Webb. because now you see the astronomers are, able to observe or have indications of being able to look at objects at high Z into the teens. I think like Z's of 7 or 8 were somewhat limiting up till about maybe 10 years ago, maybe 15 years ago. But I think that's starting to grow, and they're starting to see these higher numbers. I don't know how high it can go,
think the
because
I
like you say,
think
it's
I've
hard
seen
to.
11 or 12
Bernie?
already.
Bernie, I know there is a direct relation, there is an equation that goes from Z to V, to this recessional velocity here. There is an equation that goes from Z to V, because that's how they measure V, is they look at the redshift, the Z number. There is a relationship between Z and V, and then you can see here, from once you got V, you can go directly to D.
Yeah,
So
I'll
there
keep
there-
looking.
Yeah.
Hopefully I'll run across something someday.
But I can tell you this, the relationship between Z and V is not linear. Because
No, definitely not.
it's spectral.
And also, I believe with some of the stuff from Webb, the highest Z value they have right now is, I think, 13.1.
Right.
Which is about 3, I want to say, coming close to between 3 and 500 million years after the Big Bang in terms of age. So very young galaxies.
Pushing it way up.
For context, it took about the first 300 million years of the universe. It's opaque to us because of ionization. The universe was too hot for light to travel through it and had to cool down a little bit. So I don't think we'll see anything from Webb crossing that 300 million year old barrier. For that, you have to go to the cosmic microwave background.
So I have a question or
Go.
an observation. So back to your star party.
Oh.
If you're out at a star party and you say the Andromeda galaxy is 2.5 million light years away, isn't that right?
Whatever.
And somebody said, and you have a student say, well, how do you know that?
Well,
So you could say,
Tell
well,
them- you
Paul
can tell
figured
them-
it out.
tell them Cepheid variables.
Yeah, Cepheid variable, but because it just depends on how much detail they want,
Yeah.
I guess. You can tell them you can figure out distances with using trigonometry, which would probably turn a lot of people off, or that they've discovered ways to figure it out. Depends on how much detail they want, I guess.
Parallax
I mean,
is
basically, if somebody were to come up to me at a star party and say, and if I said, okay, I that star is like 40 light years away, and they say, well, how do you know how far away it is? I'd say, well, we can measure it with parallax, and I would tell them real quick what parallax is. But then if someone says, like you said, how far away is the Andromeda galaxy? And I say 2.5 million light years, and they say, well, how do you know that? I would say Cepheid variables, and I could explain to them what the thing is with Cepheid variables. And then if they talked about, galaxies that were a lot farther away, then, you can go to Hubble's law.
So to give kind of a more down-to-earth explanation for those that do engage in star parties, the way you can explain parallax is tell someone to hold one of their fingers up in front of their eyes, in
Yes.
front of their face,
Look
and
at it with the
close
right
one
look at it
eye,
with the left eye, and you'll
and
see
then
it
close
there.
the other eye, and you'll see that your finger will move slightly.
Yes,
That's parallax.
correct. And you just say what astronomers do is they use an observation at one time of the year and then look at it again 6 months later. And that baseline is 180 million miles. Any other questions?
You think there's a possibility of a future presentation on the Z versus V?
That would probably be a little bit much for this group.
That's
That gets into some
kind
heavy
of-
math.
Mhm.
Yeah, that
Not
gets
exactly
into the heavy
amateur.
math, because I remember doing that math in graduate school. I remember computing recessional velocities off of redshifts. Yeah, that involves some math. I don't think that would be appropriate for fundamentals group.
Maybe you need another special interest group for physicists.
Remember, this is an amateur astronomy club, not a,
Not an amateur physics club.
yes,
No,
well,
but we
and
have quite a
not-
few people in the club who understand a lot of that stuff. Like my
and
husband, you know.
I'm not saying they don't there. I'm just
Yeah.
saying that it's hard to digest. It needs a
Yeah.
lot of background to it. And in
People-
general, I like to think we try to keep these presentations to around the high school level. And that's certainly pushing it into the senior graduate, the senior undergraduate versus early graduate school level.
I mean, this is fundamentals interest group. Those formulas that take redshift and compute a radial velocity from it are all available in the textbooks, and are certainly, you could find it online if anyone really wants to know.
Thanks.
Hey Doug,
Yeah,
how do you suppose they measured the angles back in Eratosthenes' days without benefit of telescopes or photographic plates or whatever?
well, I mean, Hipparchus, okay, I mean, let's go back. This image that I got actually is a pretty good image. See what he's doing there? This is a painting, a diagram that I found of Hipparchus doing some astronomical observations at his observatory. At that time, this was Cairo. He was in, not Cairo, Alexandria. And he's got an armillary sphere behind him, and he's got another device, which I don't know what it's for exactly, but you see that he's looking through this long tube. Obviously, it's not a telescope. Telescopes were not invented, but he's looking through this very long, narrow tube, which allows him, he can pinpoint position of a star, and he would mark it down on a chart, and he's trying to do parallax, so he's looking for a shift. So he would look at the star at one time of night and then go out and then look at it again 10 hours or 12 hours later, knowing that he could use the diameter of the Earth as his baseline for his trigonometry. And he wouldn't see any shift, obviously, because the stars are too far away. But this is what he's looking for. He's looking for that shift because he's comparing it. He's looking at one star, and he's got another background star in the same field of view, if you like, and he's looking to see if there's any kind of a noticeable shift. But like I said, he wasn't able to come up with anything because no telescope, too small baseline.
So we assume that his instrumentation is really good in that he can record a position, then 6 months later.
He was looking 6 months later, more like 6 hours later.
6 hours or 10 hours, 12
Oh,
hours.
I thought you had to wait.
So
No,
modern days,
because the Greeks, while Eratosthenes had been able to compute the diameter of the Earth fairly accurately, no one had computed the orbit of the Earth yet. They did not know. Like Aristotle had come up with the idea that he thought the Earth went around the sun, but he was laughed at for that. And they hadn't really computed what the radius of the orbit was. So they could not use that as a baseline for their parallax. Hipparchus used the diameter of the Earth as his baseline. He would do a measurement at one time of night and another measurement 12 hours later. Okay, and then he would use the diameter of the Earth as the baseline. So clearly he was not getting anything. He was not seeing any shift at all, because the shift, like I said, would have been milliarc seconds at most. And he didn't have a telescope, so the closest measurements he could get was probably minutes of arc, a few minutes of arc he could get in terms of an angular shift that he could see, which, like I said, they were able to measure distances to planets, to some of the planets, because that's close enough where you could get a shift of a couple of minutes of arc. And they were able to do that. They were able to measure the distance to the moon and the closer bodies, but not any stars.
You may have mentioned this, Doug, but how accurate were their measurements to the planets?
Some of them were pretty good, not all of them. In a couple of cases, they got within 10%.
Not bad.
But in some of the other planets, they didn't do quite as well.
think
But
it's
they had
Saturn.
estimates. They had estimates.
Take it Saturn and Jupiter were the outliers, given.
Yeah. Yeah, they had a good estimate for Mars. That's the one that was, I think, 10%. But yeah, as they got farther away, of course, it got harder.
I think recession threw them off a lot too.
But considering that they didn't have telescopes, I think they did quite well. And that they didn't, also considering that they didn't understand Newtonian mechanics, or, they didn't understand the orbits. They did rather well with their distances. Eratosthenes' estimate of the diameter of the Earth was a few percent. Okay, I'm going to stop sharing.
And thank you very much, Doug. Before we wrap up for the evening, any other questions or comments before I dismiss? Thank you all very much for attending. I don't have any announcements about what's going to be on the table for next month. I need to get with the other presenter and sort that out. So look forward to that in the next month's club bulletin. Not club bulletin, the next meeting agenda I send out. So thank you, everybody. See you in a month.
Good job, guys.
Thank you. Take care.
Night.